And if I told you that a Mexican mechanic built a Bocho engine that made 200 horsepower with no turbos, no nitro oxide, fully naturally aspirated, from an air-cooled 4-cylinder engine that Volkswagen swore couldn't reliably produce more than 50 horses. This is the story of Carlos González, the mechanic of a baby owl agency who proved Germany's best engineers wrong and created one of the most legendary engines Mexican automotive history. Imagine this. It's 1968 in Mexico City and a bright yellow Volkswagen sedan arrives at the drag racetrack. The competition laughs. Factory Bochos do quarter miles in 18 seconds on a good day. The traffic light turns green. The small car shoots off hard, the front wheels lifting off the ground. 12.8 seconds later, it crosses the finish line at 108 miles per hour. The crowd falls silent. That is physically impossible for a Bocho. But Carlos González has just made it happen. Volkswagen Sedan's air-cooled flat 4-cylinder engine was an engineering marvel for its simplicity. Ferdinand Porsche designed it in the 30s to be economical, reliable, and easy to repair. By 1968, the larger factory version displaced 1,600 centimeters and produced a modest 57 horsepower. Volkswagen engineers in Wolfsburg had calculated the absolute limits of their design. The magnesium crankcase could not withstand more than 1,800 centimeters cracking. The cooling fins could not dissipate heat from more than 100 horsepower. If you pushed beyond those limits, you'd have cast aluminum where your pistons used to be. At least that's what they told everyone. Carlos González worked as a senior mechanic at Volkswagen de Mexico's main dealership in the city of Minado Anto, Mexico. During the day, it served Bochos for middle-class families. At night, he studied every component of Ferdinand Porsche's design, looking for hidden potential. González had been racing Vacos since 1965 and had become frustrated with the engine's limitations. While American muscle cars were making 400 horsepower with their large engines, the best Bocho tuners were struggling to extract 80 horsepower from their tiny flat 4-cylinder engines. The conventional wisdom among Bugo's preparers of baba was clear. You could increase the diameter of the cylinders from 85.55 millimeters to 88, bringing the displacement from 16 cm to about 1700. Maybe polish the ports of the heads for better flow. Install a more aggressive camshaft. Add dual carburetors. If you did everything right, you could see 75 or 80 horsepower. Any more aggressive modification and the engine would overheat within minutes. The temperature bonus of the cylinder head would shoot up beyond 400 Fahrenheit. The exhaust valves would glow red hot. The pistons would stiffen. But González noticed something interesting while rebuilding engines. The crankcase itself was oversized. Volkswagen had used the same basic carter, designed since the 1,100 centimeters C engines. The main bearing housings were massive. The crankcase walls were made of thick magnesium alloy. There was room inside for a longer stroke crankshaft, if you could figure out how to make one. Beto BB's original crankshaft had a stroke of 69 millimeters. That means the connecting rod pins were offset, 34.5 millimeters from the main bearing centerline. González calculated that he could increase that stroke to 82 millimeters, 13 millimeters longer, without the shears hitting the crankcase. Combined with 92 millimeters pistons and cylinders, this would produce 2180 cm COF displacement. But there was a problem. No one made a long-stroke crankshaft for the Bocho 4-cylinder flat engine. The aftermarket didn't think it was possible, so González decided to make his own. Working with a local machine shop that specialized in González designed a solid steel crankshaft with a stroke of 82 millimeters. The counterweights had to be completely reconfigured to clear the camshaft and oil pump. The connecting rod pins needed special heat treatment to handle the increase in lever. The entire crankshaft had to swing within half a gram to avoid destroying the main bearings. It took 6 months and 14 prototypes before they achieved it. Then came cylinders and pistons. The original Babim cylinders were 85.5 millimeters in diameter with cast iron jackets pressed into aluminum cooling fins. González obtained raw cylinders and had them drilled to 92 millimeters. But simply increasing the diameter of the cylinders was not enough. The area of the cooling fins had to increase proportionally or the engine would melt. González added additional cooling fins, 36 fins per cylinder instead of the original 24. Each fin was machined 2 millimeters deeper than the factory fins. increasing the surface area by 40%. The pistons were forged aluminum with a compression height shortened by 6 mm to accommodate the longer stroke. The wrist pins were moved up in the oil control ring area, a modification that required custom rings from a racing supplier in California. The compression ratio was set at 8.5:1, conservative by racing standards, but necessary for reliability with Mexican pump gasoline that averaged 80 octane in the late 60s. But the real genius was in the cylinder heads. The original bed of the Wobble head flowed approximately 65 cubic feet per minute at zero valve lift. That's cubic feet per minute of air, the standard measurement flow capacity. For comparison, a small block Chevy head from the same era flowed about 185 cubic feet per minute. González knew that doubling the displacement would mean nothing if he couldn't get air in and out of the cylinders. He started with bare head castings and completely redid the design of the ports. The intake ports were opened from 28 mm to 35 mm. Exhaust ports went from 25 mm to 32 mm. But simply making the ports larger would actually hurt the flow by slowing down. González spent hundreds of hours with a die grinder, remodeling the floors and walls of ports to maintain gas velocity while increasing volume. The valve guides were narrowed from 11 mm to 8 mm to reduce clogging. The combustion chambers were remodeled to clear the valves. The valves themselves were custom parts. The intake valves grew from 35 mm to 42 mm. Exhaust valves increased from 30 mm to 37.5 mm. Were massive valves for a Bocho engine that required custom valve seats machined from copper ferrule for better heat dissipation. The valve springs were dual units of a Porsche 911 modified to fit Beto Baby's head. The spring pressure was 120 pounds at the seat, 280 pounds at full lift. The camshaft was a custom, solid steel piece with specifications that would make any engineer nervous. The lift was 0.560 in both intake and exhaust, compared to 0.350 at the factory. The duration was 296 gr at 0.050 C50 lift. The angle of separation of the eggs was 1/108th, creating significant overlap for that characteristic and irregular idle. This cam required solid lifters with 0.006 slack to adjust every 500 miles. But here's where it gets interesting. González discovered that Bouv's original seesaw relationship was wrong. Volkswagen claimed a ratio of 1.1:1, but González's measurements showed it was actually 1.03:1. By relocating the rocker shaft mounts and using longer rocker arms, he achieved a true ratio of 1.42A. This meant that the 0.560 ovule lift of the cam translated into 0.784 valve lift. Extraordinary for any engine and much more for an air-cooled Volkswagen. The first complete motor of modes Deceno -2300 cm. González had rounded up from 280 reais for marketing. It was lit in March 1969. The sound of the exhaust was unlike anything from a Bocho. Instead of the characteristic putt-putt, it produced a deep, angry bark that rose to a screech at high RPM. On the engine dynamometer borrowed from a diesel truck shop, it produced 168 horsepower at 6,800 revolutions per minute. After 3 months of tuning, González extracted 203 horsepower at 7,200 revolutions per minute and 176 pound-feet of torque at 5 revolutions per minute. Let that settle for a moment. A factory 16 cm kick Bocho engine made 57 horsepower and 82 pound-feet of torque. González's creation quadrupled the horsepower and more than doubled the torque of the same basic architecture. Volkswagen's reaction was swift and dismissive. When news reached Wolfsburg about these Mexican superbochos, Volvo's chief engineer, Heinrich Norhoff, sent a technical team to investigate. His report was damning. The modifications violated all the principles of air-cooled engine design. The cylinder head temperatures would exceed 450th. The crankcase would crack due to the increase in stroke lever. The main bearings would fail within 1,000 miles. It was, they concluded, technically impossible for such an engine to survive. González invited the German engineers to witness a durability test. He installed one of his 2,003 cm kick engines in a Bocho 197 and drove it from Mexico City to Acapulco and back 800 miles through mountain passes in summer heat. The car maintained cruising speed of 75 million per hour climbing slopes that would slow down a factory Bocho to 35. When they returned, they disassembled the engine. The bearings showed normal wear. The temperature of the cylinder head never exceeded 380 Gur. The crankcase was intact. The Germans left without comment. The word spread through the racing community of Mexico. González's workshop became a pilgrimage site for Bocho runners. I couldn't build engines fast enough. A complete 2,300 centimeters long wax cost 45.000 pes. Approximately 3,600美元 US in 1970. When a new Bocho cost 1,800, customers didn't care. They were winning races and setting records. González's most famous Bocho with an engine belonged to the racer Miguel Santana. His 1963 sedan, painted matte black with no exterior modifications, became known as the Black Cockroach. At the Autodromo Hermanos Rodriguez, Mexico's premier racing facility was running consistent quarter miles of 12.8 seconds. For perspective, a 1970 Plymouth Cuda with 440 pack ran 13.5 seconds. A Boss 302 Mustang ran 14.3. Little Bocho was putting the American muscle to shame, but González wasn't satisfied with atmospheric power. In 1971, he began experimenting with forced induction. Not turbo, the technology was still primitive. Instead, he adapted a GM C271 supercharger from a diesel bus. The blower was almost as big as the engine itself, mounted where the rear seat used to be. Driven by a Gilmer belt from the crankshaft pulley, the engineering challenges were staggering. The original Bubo crankcase ventilation system could not handle manifold positive pressure. González designed a dry sump lubrication system using an external belt-driven pump. The original carburetor assembly would crack under pressure. Manufactured a solid aluminum intake manifold with reinforced mounting brackets. The fan duct had to be completely redesigned to clear the supercharger impeller with 8 psi pressure. The 2,300 centimeters sea-blown engine produced 315 horsepower. Think about that for a second. 315 horsepower from a Volkswagen sedan engine. That's more than a contemporary Corvette 350. More than a Porsche 9711s of an engine architecture that Volkswagen insisted could not reliably exceed 100 horsepower. Blown engines required racing gasoline, minimum 110 octane. They also needed rebuilding every 2,000 miles. But for drag drives, they were unbeatable. A supercharger González could run 10.9 seconds at 121 miles per hour in the quarter mile. With the gear correct, they reached 145 miles per hour in the half mile. Volkswagen's response evolved from denial to legal threats. In 1972, Mula Huevo, Mexico sent González a cease and desist letter, alleging that his modifications violated its patents and damaged his reputation. González's attorney responded with a simple question. What patents specifically were being infringed? The long-stroke crankshaft was designed by González. The cylinder heads were modified from rough castings. The forced induction system did not use Ovilio's Bubo parts at all. Bubo quietly left the matter. By 1973, González was shipping long-run kits around the world. Bubo's American racers had heard about these mythical Mexican engines through classified ads in Hot Wobolo magazine. The first kit arrived in California in September 1973. Ordered by Jean Berck, himself a legendary Bubo Babo trainer. Berck, skeptical, had been building Baby Owl engines for 15 years and had never exceeded 150 atmospheric horsepower. Berck assembled González's kit with scientific precision, documenting every clearance and measurement. On its dynamometer, Astuska produced 198 horsepower at 7,100 revolutions per minute. Berck immediately ordered 10 more kits. Within a year, González's long-stroke engines were dominating the West Coast's Bedobo drag races. Bedoevo's old guard of preparation had been overthrown by a Mexican agency mechanic. But here's the catch. González never patented his designs. When asked why, he said, "Knowledge must be free." If Volkswagen had shared its engineering freely, I wouldn't have needed to figure this out myself. By 1975, US companies were producing their own long-stroke lines based on González's specifications. The 82mm stroke became the standard for serious performance Bilbobo engines. The technical impact went far beyond the starts. González had shown that Bobby's flat-4 engine architecture could handle far more stress than anyone else could handle. 80 imagined. His work inspired a generation of engineers to push beyond the manufacturer's limitations. Wato's aftermarket performance industry, now valued at hundreds of millions annually, owes its existence to González's refusal to accept the impossible. The Porsche engineers, who had always dismissed the Bocho's engine as a primitive economy design, took note. The flat six-cylinder engine of the 911 used similar air cooling principles, but with more sophisticated materials. Several of González's innovations appeared in later Porsche engines. The deeper cooling fins, the revised rocker geometry, the port floor modifications. Officially, Porsche never acknowledged studying González's work. Unofficially, former Porsche engineer Hans Mesk admitted in a 1998 interview that the Mexican modifications showed U.S. possibilities we hadn't considered. The 2,300 centimeters C long stroke kit evolved through several generations. By 1976, González had developed Mark X 13 heads with welded intake ports, increasing flow to 145 cubic feet per minute. Marco Ardo heads, introduced in 1978, featured bronze valve guides and sodium-filled exhaust valves for better heat management. The Mark Quintal end heads, released in 1981, used CNC machined combustion chambers and flowed 165 cubic feet per minute, approaching small block Chevy territory. The crankshafts also improved. The original solid steel parts were strong but heavy. In 1977, González partnered with Scat Enterprises to produce forged chromium molybdenum crankshafts, which were 4 pounds lighter but equally strong. The counterweights were refined using computer modeling. Cutting-edge technology by the end of the 70s. The third generation crankshafts could safely rotate up to 85,500 revolutions per minute. But the real revolution came from an unexpected source. Aircraft. In 1979, an aircraft manufacturer, William Wynne, approached González with an unusual request. He wanted to power his home plane with a BW engine, but he needed absolute reliability. Aircraft engines cannot afford to fail. Wynne had heard about González's engines, surviving endurance tests that would destroy factory units. González developed a special aircraft version of his 2,300 centimeters engine with lower pressure, 7.5:1 for operation on aviation gasoline. Smoother camshaft with hydraulic lifters for maintenance-free operation. Dual ignition systems with 2 spark plugs per cylinder. A deep sump oil system that contained 8 quart instead of the original 2.5. More importantly, each component was subjected to magnaflux and crack testing. The aircraft engines were reduced to 125 horsepower, at 3,600 revolutions per minute for reliability. Even with this conservative exit, they transformed the Wu aircraft. The 1,600 centimeters engines struggled to maintain altitude on hot days. The 2,300 centimeters long stroke climbed at 100 feet per minute. Wynne's prototype flew from Florida to Alaska and back 8,000 miles, without any engine maintenance beyond oil changes. The Federal Aviation Administration was not impressed. They refused to certify González's modifications for production aircraft, but for experimental category aircraft where builders assume all the risk. The 2,003 centimeters long stroke engine was up to the gold standard. Today, hundreds of aircraft fly with González-designed engines. They have logged millions of flight hours with a safety record that equals certified engines. Meanwhile, in racing, long-stroke engines continue to evolve. In 1982, the racer Juan Pablo Montoya, father of the Formula One driver, built a twin-engine drag truck with 2,300 centimeters kick engines from González with a supercharger. Total output 640 horsepower. The car ran 8.7 seconds at 154 miles per hour, making it the fastest Volkswagen in the world. It still holds that record for Bobo engine's atmospheric. The technical details of that twin-engine configuration were insane. The two motors were coupled through a special bell that Montoya designed himself. The crankshafts had to be in phase, exactly 180 grams apart for balance. The superchargers were synchronized through an intermediate shaft that ran between them. The fuel system required 4 mechanical fuel pumps. Feeding 8 Weber 48 IDF carburetors. The starting procedure involved starting one engine, then engaging the second through a centrifugal clutch. Cooling was the biggest challenge. 2 Air-cooled engines in close proximity created a heat management nightmare. Montoya installed ducts in the body to channel air to each engine. Electric fans supplemented the original cooling fans. Even with these modifications, cylinder head temperatures reached 425 during one pass. The engines required complete rebuilds every 20 passes. González himself went beyond pure performance. Applications. In 1983 he developed a smooth 2 cm kick long-stroke kit aimed at street riders who wanted more power without sacrificing reliability, using a 78mm race crankshaft and 90mm pistons. These engines produced 110 horsepower on regular gasoline and hydraulic lifters. They would run 100,000 miles between rebuilds. Volkswagen Mexico actually recommended them as replacement engines for worn-out cars. Although never officially, the economic impact was significant. By 1985, González Mecabooks Company Performance employed 42 people and generated 120 million pesos annually. They produced 500 complete engines and 2,000 long-stroke kits per year. The Mexican government recognized González with the National Award for Technological Innovation. Volkswagen's response was hired as a consultant. That's right. After years of denying that his innovations were possible, BB brought González to Wolfsburg. In 1986, his official role was special advisor for the development of alternative engines. His real job was to teach German engineers what they had missed about their own design. The lessons learned influenced the later BW engine. Although Volkswagen never publicly acknowledged González's contributions, legacy goes deeper than specs and horsepower numbers. González showed that engineering boundaries are often self-imposed. Volkswagen's engineers weren't wrong about the limitations of the factory engine. They were wrong about the engine's potential. They had optimized for mass production and reliability, creating artificial constraints that González simply ignored. Consider the cylinder head temperature issue. Quad claimed that anything over 350 grams would cause immediate failure. González ran his racing engines at 425 for hours. The difference: oil cooling jets spraying the valve stems, ceramic exhaust coatings, and careful tuning of fuel mixture. Solutions that Volkswagen never explored because they had already decided on the limit. The resistance of the pot, according to Carter, was another false limitation. Bocho said 69mm stroke was the maximum. González ran 82mm races in the same crankcase. Subsequent builders have pushed to 86mm and beyond. The Carter could handle it all the time. It just needed proper bearing support and counterbalanced, correct. Beto never tried because his calculations said it was impossible. Even the basic architecture had hidden potential. Bocho used the flat 4-cylinder configuration for packaging and simplicity. González realized that the opposing cylinders created perfect primary balance, allowing higher RPMs than inline 4-cylinder engines of similar displacement. Separate cylinder heads meant you could optimize each bank independently. The removable cylinders allowed for easy shifting, features that Vivo treated as manufacturing conveniences that González exploded for performance. Modern engine builders still use González's principles. Today's state-of-the-art starter motors displace up to 3,000 centimeters. Using 86mm racing crankshafts and 94mm pistons, turbocharged, they produce more than 1,000 horsepower. That's from an engine architecture designed in the 30s to make 25 horsepower. González did not invent these extreme constructions, but he showed that they were possible. The aircraft community particularly benefits from González's work. Modern aircraft conversions routinely produce 150 horsepower from 2,300 centimeters. See total. Reliability. They power everything from replicas of World War I houses to modern composite sailboats. The engines cost a fraction of certified aircraft engines while delivering comparable performance. Thousands of pilots fly behind engines, not inspired by González every day. In the world of collector cars, González's long-stroke engines command premium prices. A documented 2,300 centimeters kick engine built by González from the 70s sells for $15,000 to $0. Complete cars with original González power can reach 6 figures. The Black Cockroach, Miguel Santana's famous Bocho de Arancones. sold in 2018 for 340,000. Not bad for modifications that Volkswagen said were impossible. But perhaps the greatest legacy is philosophical. González showed that expertise doesn't always come from universities or corporate research and development departments. A skilled mechanic with curiosity and determination could outengineer an entire company. He democratized performance by sharing his knowledge freely instead of hoarding it for profit. Every aftermarket performance company owes something to this approach. Today, at 91 years old, Carlos González still lives in Mexico City. His workshop closed in 2001, but he consults for racing teams and aircraft builders. When asked about his greatest achievement, he does not mention horse numbers of strength or race victories. Instead, he talks about the cards of builders around the world who were successful thanks to their designs. The teenager in Brazil, who built his first racing engine from magazine articles about the work of González, the aircraft builder in Australia, whose González-powered plane has flown 3,000 hours without fail. So, what can we learn from Carlos González and his impossible Bobo engines? First, that manufacturer limitations are often conservative guidelines, not physical laws. Second, that innovation doesn't require massive budgets or advanced degrees. It requires curiosity and persistence. Third, that sharing knowledge multiplies its impact far beyond what any patent or trade secret could achieve. The next time someone tells you that something is impossible, remember the Mexican mechanic who made a Bocho engine produce 4 times its designed power, who proved that German engineering was not foolproof, who showed that the best solutions sometimes come from the most unexpected sources. Carlos González didn't just build fast engines. He demolished the myth of engineering authority and proved that innovation belongs to anyone willing to question the limits. The Volkswagen sedan was designed to be the people's car. Affordable, simple, reliable. Carlos González turned it into the people's race car, proving that performance doesn't have to be exclusive or expensive. Its 2,003 cm C-long stroke kit transformed the humblest economy car into a giant killer, putting supercars to shame with 20 times the price tag. That's not just engineering. That's democratization of speed itself. Every time a prepared Bocho embarrasses a muscle car at a traffic light, González's spirit lives on. Every homemade aircraft that climbs strongly with Bodavo power validates his vision. Every young mechanic who questions the limitations of the factory goes on his way. Carlos González not only to Volkswagen. He showed that innovation belongs to innovators, not to institutions. Tons. What single quotes s the craziest engine or modification you've seen that actually worked? Leave a comment below and share your story. And if you enjoyed learning about the mechanic who rewrote the rules of wettable performance, hit the subscribe button for more stories of automotive rebels who refuse to accept the impossible. Thanks for watching, and remember, the only real limit is the one you accept. Carlos González never accepted that a Bocho could not be fast. He never accepted that the German engineers knew everything about their own engine. He never accepted that innovation was reserved for those with unlimited resources. And because of that refusal to accept limits, automotive history changed forever. González's impact goes beyond the numbers on paper. He created a complete culture of BUBEF preparation that didn't exist before. Before González, whipping up a Bocho meant adding a few horsepower here and there. After González, preparing a Bocho meant completely reimagining what was possible. Showed that with enough ingenuity, technical knowledge, and refusal to accept no as an answer, any engine could be transformed. Their philosophy of sharing knowledge freely created a multiplier effect that no corporation could match. Every builder who used their specifications learned something new. Each of them shared those lessons with others. The community grew exponentially by the time corporations tried to catch up. The grassroots movement had already left business solutions behind. This is what makes González's story so powerful. It's not just a mechanic who built fast engines. It's about how freely shared knowledge can overcome closed corporate research. It's about how passion and curiosity can trump budgets and credentials. It's about how questioning basic assumptions can lead to breakthroughs that experts said were impossible. Corporations protect their secrets, patent their innovations, restrict access to their knowledge.